Okay. Good afternoon, ma'am. We're Group 3 from your COE119L Assembly Language Laboratory class. We are here to present our design of experiment, which is entitled Security Alarm System using Atmega 32 Microcontroller and Assembly Language Program. As you can see here, this is our working prototype. The inputs are the PIR sensor or the motion sensor. Once you put or wave a hand, the output will be transferred into the servo motor.
I'm Rap Noel Ang, and I'm here to introduce to you the body of the codes. So here, as you can
And okay, so here in Interrupt 20, this red D is to set up the servo. This one is to prevent the device from hanging up. This is the main body of the program. This line will the RP0 be equals to 1. Next, RP1 is equal to 0. Then RP1 to RP0 is equals to bank 1 to call the trace A and trace B. Move, move low H00. We put 00 to accumulator W and 00 data is prepared. Move trace A. It will write the contents of the W register into the trace A register. Next, this move low P0000010 is to we put the the bit value to accumulator and then the data is prepared. Here it will write the content of the W register or the accumulator. This one it has assigned the bit value to W. Next, move WF add con 1. This one configures as analog or digital input output. In this case, in our photo, the value in W will be moved to add con 1, which set port A as a digital input. PCF status RP0. RP0 is now equal to 0. Then RP1 is to RP0. Bank is now equal to bank 0 is to call port A. RP1 is to RP0 equals bank 0 to call port A and port C. Now, this is for the checking. This line, check bit 1 of port B if it's set to 1 and skip the next line if the bit is 0. And this one, and it's also check the bit 1 of port B if it's set to 1 and skip the next line if the bit is 1. Now, go to node detection. If bit 1 is set to 0, it will call the subordinate node detection. And in vice versa, if bit 1 is set to 1, it will call the subroutine move. And now go to checking again. For node detection, this line, we put the bit value 00010 to the accumulator. 00 data is prepared. And this one, it will write the content of the W register, the bit value, this one, into the port A register. Stop the movement of the servo and the sound of the buzzer. And now, go to the checking again. Now here, from the move stages. In this, it clears the bit 1 of port A to 0, which turned off the red LED. This one set the bit 2 of port A to 1, which is also lights up the green LED. Sets the bit 3 of port A to 1, which sounds the buzzer. In this part, this line, we put 30 to accumulator W, and then the 00 data is prepared. Move WFD1. It will write the content of the W register 0001 1110 into D1 memory address. call loop 0. Since we use C block, we can call loop 0 with a content of D1. In here, we put 32 W accumulator, 00 data is prepared. Next line, it will write the content of the W register into D2 memory address. And in there, since we use C block, we can call loop 90 with the content of D2. Over here, we put 30 to accumulator and then 00 data is prepared. It will write the content of the W register into D1 memory address. Since we use C block, we can call loop 0x with the content of D1. And now we go to checking again. Loop stages. After the call loop 0x or loop 0 and call 90, this one will this loop 0, okay, after the call loop 0x. In here, the loop 0x the loop 0x set RA0 equals to 1 and then give the delay of 0.5 milliseconds with RA0 equals to 1. Then we can call delay 18 milliseconds with RA0 equals to 0. Since we use C block, we can do that. Again, since we use C block, we can reduce the number of bits until the D1 equals F in here. Then it will go back to loop 0x and then return and go back to checking. In loop 0, we set the RA0 equals to 1. Then it will give a delay of 0.0 milliseconds with RA0 equals to 1. Here, set RA0 equals to 0 and then it can call a delay of 18 milliseconds with RA0 equals to 0. Again, since we use C block, we can reduce the number of bits until D1 equals F. Go back to loop 0 and then return. And now it's for the loop 90. Here, let's set the RA0 equals to 1. Then we can call a delay of 1.5 milliseconds with RA0 equals to 1. Again, RA0 equals to 0. We set RA0 equals to 0. Then it gives a delay of 18 milliseconds with RA0 equals to 0. Since we use C block, we can reach the number of bits until the D2 equals F. Then go back to loop 90 and then return.
So I'm Norman David Kinikini. I'll be discussing the delay stages. So here, the delay stages, we set the delay to 0.5 ms or 500 ms equals to 0 degrees. Next line, we put 5A to W accumulator. 5A data is prepared. Next line, it will write the contents of the W register 0101 1010 into DC9 or the memory address. Next line, since we use C block, we can reduce the number of bits until the DC is equal to F. DC9 is equal to F. Next line, since we use C block, we can call DR with the value of DC9. Next line, since we use C block again, we can reduce the number of bits until the DC10 is equal to F. So the next line will be the process where we can call the DR with the value of DC10. So next delay. The next delay is 1.5 ms. We set 1.5 ms or 1500 milliseconds equals to 90 degrees. Next line,
we put 3F to W, which is an accumulator. 3F data is prepared. So it will write in this line, it will write the contents of the W register 010011111 into DC2 or memory address. Next line is that we will be putting 22W accumulator. 20 data is prepared. So it will write the contents of the W register 0010 000 into DC3 or the memory address. Next line, since we use again C block, we can reduce the number of bits until the DC2 is equal to F. Next line, since we use C block, we can call dy with the value of DC2. Then we can get and reduce the number of bits until DC3 is equal to F. Then since we use again C block, we can call dy with the value of DC3 now. For the next delay, we put delay 3ms or 3ms for 180 degrees. For the first line, we put F1 to W accumulator. So FF data is prepared, or 1F. It will write now the contents of W register 111 111 into DC memory address. We put 40 to W accumulator so that the 40 data is prepared. Next time, it will write the contents of the W register 01000000 into DC3 memory address. So next line, since we use C block again, we can reduce the number of bits of DC2 is equal to F. Then next line, we can call DJ with the value of DC2. Then we can reduce again the value of the number of the bits until DC3 is equal to F. Then we can call now DC with the value of DC3. For delay 2 seconds, we put FFF to W accumulator, which prepared the data of FF, which prepared FFF data. Now it will write the contents of the W register to 111 1111 into DC6 memory address. Now we put FFF to W accumulator so that the FFF data is prepared. Then it will write the contents of the W register 1111 1111 into DC7 memory address. Now we put A0 to W accumulator, so A0 data is prepared. Then it will write the contents of the W register 1010 0000 into DC8 memory address. Since we use C block, we can reduce the number of bits until DC6 is equal to F. Then we can call DL with the value of D6. Then reduce again the number of bits until DC7 is equal to F. Then call DL with the value of DC7. So we can call DL with the value of DC7. Next, we can reduce the number of bits until DC8 is equal to F. Then call DL with the value of DC8. Now for the next delay 18 milliseconds, we put FF to accumulator W. Now FF data is prepared. It will write the contents of W register 111 1111 into DC4 memory address. So in this line, we put 81 to W accumulator, 81 data is prepared now. It will write the contents of the W register 10000001 into DC5 memory address. Here, we will be reducing again the number of bits until DC4 is equal to F. Then we can call DS with the value of DC4. Then we can reduce again the number of bits until DC5 is equal to F. Then we can call again the DS with the new value of DC5. So for the last delay, for the second to the last delay, we use delay 1 second. So we put 44 to W accumulator. So 44 data is now prepared. It will write the contents of the W register to 0100 into D6 memory address. Now we put 32 to W accumulator. So 32 is now prepared. So the contents of the W register 0011 into D7. So next line. Here, we put 62 W accumulator. So 60 data is prepared. It will write the contents of the W register 0110 into DC8 memory address. Next, we use again C block. So we can reduce now the value of the number of bits until DC6 is equal to F. Then we can call DLX with the value of DC6. Then we can reduce again the number of bits until the DC7 is equal to 7. Then the new value of DLX is DC7. Then reduce again until the DC8 is equal to F. Then we can call again the value of DCLX to the new value, which is the DC8. For the last delay, we use delay 0.5 seconds. So we put AAA to W accumulator. So AAA data is now prepared. It will write the contents of the W register 100 into DC6 memory address. We put FFF to accumulator. So FFF data is now prepared. So it will write the contents of DC7. It will write the contents of the W register. It will write the contents of the W register 111 into DC7. We put 50 to W accumulator. So 50 data is now prepared. It will write again the contents of the W register 0101 to 0000 into DC8 memory address. So lastly, we can reduce now the number of bits until DC6 is equal to F. Then we can call DLXS with the new value of DC6. Then reduce again the number of bits until DC7 is equal to F. Then with the new value of DLX, we can call it with the value of DC7. Then reduce again the value or the number of bits until DC8 is equal to F. Then call DLXS with the new value of DC8. That's the end of the program and how it works. So let's copy paste the code to MPLab. Let's build the program. So as you can see, there's no the build succeeded. The build succeeded and ready to run. That's all. Thank you.